Okay, so the first part of the first question is to prove that for any positive integers n and r, the equation on screen is true. So first we need to recall what NCR means. So NCR is equal to n factorial over r factorial multiplied by n minus r factorial. So considering we have all these NCRs, the best thing to do first would be to write out the different NCRs. So for example, we have n plus r c r plus 1, and this would be equivalent to n plus r factorial divided by r plus 1 factorial times n minus 1 factorial. And so the reciprocal of this, so 1 over n plus r c r plus 1 is equal to r plus 1 factorial n minus 1 factorial divided by n plus r factorial. I won't bore you with having to seeing me having to write all the different NCRs, so I'll just skip to the screen where I've written them all out. Okay, so as you can see, I've written the relevant fractions, so 1 over n plus r minus 1 CR and 1 over n plus r CR. So if we look at the right hand side of the equation, and if we first try to simplify the value in the brackets, so we'll have r factorial n minus 1 factorial divided by n plus r minus 1 factorial minus r factorial n factorial over n plus r factorial. So clearly, if we look at the denominators, if we multiply the left fraction by n plus r, then we'll have a common denominator of n plus r factorial. So doing this will give us r factorial n minus 1 factorial n plus r minus, the brackets around the n plus r factorial n factorial divided by n plus r factorial. And if we then factorize the numerator, remembering that n factorial is the same as n times n minus 1 factorial, we will get r factorial n minus 1 factorial, and then we have the n plus r, so n plus r, and then because n factorial is n times n minus 1 factorial, we'll have to minus n, and this will all be over n plus r factorial. Now why don't we introduce the r plus 1 over r? So we're multiplying this by r plus 1 over r. This is equivalent to r factorial times n minus 1 times r divided by n plus r factorial multiplied by r plus 1 over r. And if we can, and as you can see, the r's on the top and bottom will cancel out, and remembering that r factorial times r plus 1 factorial will just be r plus 1 factorial, we get the final fraction to be r plus 1 factorial times n, sorry, got the factorial here, times n minus 1 factorial divided by n plus r factorial. And as you can see, this is the same as this fraction over here, which is 1 over n plus r cr plus 1, and that is what the left hand side of the equation is. So we have proved the equation. Okay, so the second section of the first part of the question wants us to calculate this infinite sum. And with step questions, it's always a good idea to refer to what you've done previously in the question. And so as you can see, if I scroll up, this fraction here, 1 over n plus r CR plus 1, was used in the equation that we were trying to prove. And so what it might be a good idea to do is to use this equation here, this other side of the equation here, instead of 1 over n plus r CR plus 1. Okay, so if I do that and write the sum as the sum to infinity of, from n equals 1 to infinity of r plus 1 over r times 1 over n plus r minus 1 CR minus 1 over n plus r CR. If you've done A-level further maths and you've done the method of differences as a way of summing an infinite series, this should start ringing alarm bells. So I can now take the factor of r plus 1 over r out, and this will give us r plus 1 over r times the sum from n equals 1 to infinity of 1 over n plus r minus 1 CR minus 1 over n plus r CR. And so if you've done A-level further math, you should know that the way that you add these series is to write down the first couple of terms and see how they cancel each other out. So that's exactly what I'm going to do. So the first term, so if we take n equals 1, so notice we're not changing r is a fixed value, we're just changing n. So the first pair of terms will be 1 divided by RCR minus 1 over r plus 1 CR. And then we're going to be adding the next pair of terms, which will be 1 over r plus 1 CR minus 1 over r plus 2 CR. And if I continue doing this, I'll just write out two more terms. And so what we end up with is r plus 1 over r multiplied by 1 over r CR minus the limit as a tends to infinity of 1 over a plus r CR. So what we're just saying is this is the formal way of writing the limit as n in these fractions here tends to infinity. And what you should find is that a plus r CR actually tends to infinity as n tends to infinity. And if that doesn't intuitively make sense to you, think about Pascal's triangle, where as you increase the top of the C, you move down Pascal's triangle, and because we're keeping the bottom number of the C the same, we're not moving left or right. And so if you visualize it that way, the terms will start growing infinitely large. And then because 1 over infinity tends to 0 and RCR is just 1, this fraction will become r plus 1 over r times 1 minus 0, which is just equal to r plus 1 over r. The next part, when then asked to deduce that the infinite sum of n equals 2 to infinity of 1 over n plus 2 C3 is equal to a half. So we just worked out what the sum of n equals 1 to infinity is for 1 over n plus r CR plus 1. However, now we start from n equals 2, but we can easily write this in terms of the infinite sum that we previously worked out. So the sum of infinity from n equals 2 of 1 over n plus 2 C3 will just be equal to the sum to infinity of n equals 1 over n plus 2 C3 minus the first term of the sequence, which is when n equals 1. So we're just minusing 1 over 1 plus 2 is 3, so 3c3. And so this term here, if we look back at our fraction that we worked out, which was r plus 1 over r, and because clearly we're taking r here to be 2, this fraction will be equal to 2 plus 1 over 2, which is equal to 3 over 2. This fraction here, well, 3c3, because there's 3's on top and the bottom of the c, 3c3 will just be 1. So we're just minusing 1, and 3 over 2 minus 1 is equal to a half, which is the required result. Okay, so the first bit of the second part of the question asks us to prove the following, the inequality on screen for n greater than or equal to 3. So the way we are going to approach this is we are going to assume that the inequality is true, and then manipulate it into a form where the inequality that we obtain must always be true no matter what, and hence the original inequality that we started with must also be true. So first thing we're going to do is we are going to rewrite this inequality, particularly the right hand side of the inequality, to get rid of the n plus 1 c3 notation and write it in terms of factorials. So we will get 3 factorial divided by n cubed is less than, and I'm just going to write it without explaining it. If you should be able to write this by yourself. So it'll be 3 factorial multiplied by n minus 2 factorial divided by n plus 1 factorial. So the first thing we can do is cancel the 3 factorials on each side. So 1 there, 1 there. And also notice that n plus 1 factorial, so n plus 1 factorial is equal to n plus 1 times n minus 1 times n minus 2 all the way down to 1. And so this is just the same as n plus 1 times n minus 1 times n minus 2 factorial. So if I again rewrite this inequality, we will get 1 over n cubed is less than n minus 2 factorial divided by n plus 1 n minus 1 n minus 2 factorial. And this is useful because we can now cancel the n minus 2 factorials. So 1 there and 1 there. And because we know n is greater than or equal to 3, we can now start to cross multiply. And because n is greater than or equal to 3, n plus 1 n and n minus 1 will always be greater than 0. So we don't have to worry about negative numbers switching around the inequality sign. So that will give us n plus 1 n minus 1 is less than or equal to n cubed. We can also divide by n both sides because n is non-zero. So that will give us n plus 1 n minus 1 is less than n squared. And so expanding the left hand side by difference of 2 squares will give us n squared minus 1 is less than n squared. And so taking away n squared from both sides will give us minus 1 is less than 0. And clearly this is always true. Minus 1 is always less than 0. And so the inequality that we started with, which is 3 factorial over n cubed, is less than 1 over n plus 1 c3, must also always be true for n greater than or equal to 3. Okay, so the second inequality that they want us to prove that is true is that 20 over n plus 1c3 minus 1 over n plus 2c5 is less than 5 factorial divided by n cubed. So I suggest that we take the same approach with this inequality as we did with the last one. So first, let's change the n plus 1c3 notation into factorials. So doing that will give us 20 multiplied by 3 factorial n minus 2 factorial divided by n plus 1 factorial minus 5 factorial times n minus 3 factorial divided by n plus 2 factorial is less than 5 factorial divided by n cubed. So what I first noticed was that the denominators of the two fractions on the left hand side were very close to each other, and so what I did first was combine the two fractions. So we can multiply the leftmost fraction by n plus 2 on its numerator and denominator, so that its denominator has a value of n plus 2 factorial, and then we can combine the two fractions. So doing that will give us 20 times 3 factorial times n minus 2 factorial times n plus 2 minus 5 factorial times n minus 3 factorial divided by n plus 2 factorial is less than 5 factorial over n cubed. So the what I then noticed was that 20 times 3 factorial, so 20 is the same as 4 times 5, and so 4 times 5 times 3 factorial is the same as 5 times 4, then times 3 times 2 times 1, which is exactly the same as 5 factorial. So this can be written as 5 factorial, and because we have a 5 factorial in each of the terms on both sides of in each term on either side of the inequality, we can cancel the 5 factorial. So we can cancel it here, here, and here. So that will leave us with n minus 2 factorial n plus 2 minus n minus 3 factorial divided by n plus 2 factorial is less than 1 over n cubed. So if I just quickly scroll down, so this is where we are so far. So we can also factorize the numerator of the fraction on the left hand side to give us n minus 3 factorial outside the brackets, and then inside the brackets we will have n minus 2 n plus 2 minus 1 divided by n plus 2 factorial divided by 1 over n cubed. If we now simplify what's in the brackets and then cross multiply, we will end up with n minus 3 factorial times n cubed multiplied by n squared minus 5, because n minus 2 times n plus 2 is just the difference of 2 squares. That'll give us n squared minus 4 minus 1, n squared minus 5, and that's going to be less than n plus 2 factorial. So if we remember in the last inequality, or in fact in any part of the question, if we take the n minus 3 factorial and put it into the n plus 2 factorial, we can then cancel out the factorials and end up with a polynomial. So if I do that, we'll end up with n cubed n squared minus 5 is less than, so if I write n plus 2 factorial over n minus 3 factorial, and this is going to be equal to n plus 2 n plus 1 n minus 1 times n minus 2. So now we can cancel an n from both sides. So this will become n squared, and we can write the right hand side in terms of difference of two squares, in terms of two pairs of difference of two, in terms of two pairs of difference of two squares actually. So we'll get n squared minus 5 is less than n plus 2 n minus 2 multiplied by n plus 1 n minus 1. And so if we now expand all the brackets, we'll end up with n to the power of 4 minus 5n squared is less than n squared minus 4 multiplied by n squared minus 1, which is the same as, if we expand these brackets again, is the same as n to the power of 4 minus 5n squared plus 4. So we can cancel the n to the power of 4s on both sides and the minus 5n squareds on both sides. And so that'll give us 0 is greater than 4. And because 4 is always greater than 0 no matter what, our original inequality, which if I scroll all the way back up, was here, so 20, this one here. So because we ended up with 4 is greater than 0, this inequality that I have underlined must always be true. Okay, so the last part of the question reads, by summing these inequalities for n greater than or equal to 3, show that 115 over 96 is less than the sum of 1 over n cubed from n equals 1 to infinity, which in turn is less than 116 over 96. So I have written the two inequalities that we proved in the last part, and I have also written down the fact that we proved in the first part of the question. So first thing we should do is do what the question says. Sum the inequalities for n greater than or equal to 3. So I'm just going to take the first inequality, and if I write the sum notation wise, we'll get the sum of n equals 3 to infinity of 3 factorial over n cubed is less than the sum from n equals 3 to infinity of 1 over n plus 1 c3. So this looks promising because it looks like we can evaluate the right hand side of the inequality using the formula in the box. However, firstly, notice that the in the box with the summation is from n equals 1 to infinity, not from n equals 3, and although that can easily be fixed, there's another problem, which is that the c notation is n plus r, c, r plus 1. So because the bottom number is 3 in the case that we want, that means we'd have to take r equal to 2, and so we'll have n plus 2 c3, but we want n plus 1 c3. So we need to try and get around this problem and write it in the notation we want. So when if we were to carry out the summation by hand, the value that would be changing would be the top of the c expression, because firstly it'll be 4c3, then it would become 5c3, etc. The 3 is staying the same. So that means if we look back at our expression over here, because r is also a constant, that means r has to remain as 2. So that means what we need to do is somehow get the right hand side of this inequality into a form that involves n plus 2, C3. And the way that we can do that is by writing the sum from n equals 2 to infinity of 1 over n plus 2 C3. And now this is in the required form, and although it's not from n equals 1 to infinity, we actually evaluated this sum in the first part and we got that it was equal to a half. So I'm just going to quickly scroll down. Okay, so we know that the sum from n equals 3 to infinity of 3 factorial over n cubed is less than a half. But we want the sum from n equals 1 to infinity. So the way that we can do that is by adding the first terms of the sum from n equals 1 to infinity of 3 factorial over n cubed to both sides of the inequality. So that'll give us the sum from n equals 3 to infinity 3 factorial over n cubed. I'm just going to write the terms here actually. So 3 factorial over 1 plus 3 factorial over 2 cubed, which is 8, is less than 3 factorial over 1 plus 3 factorial over 8 plus half. Okay, so if we now rewrite both sides of the equation, we'll have the sum from n equals 1 to infinity of 3 factorial over n cubed is less than 29 over 4. So as I was saying, we can divide both sides of the inequality by 3 factorial, and that'll give us the sum from n equals 1 to infinity of 1 over n cubed is less than 29 over 4 times 3 factorial, which is 24. And 29 over 24, if you multiply top and bottom by 4, is 116 over 100 and over 96, which is the right-hand side of the inequality. Okay, so I've written the second inequality again, and just as we did with the first inequality, let's sum both sides from n equals 3 to infinity. So that'll give us the sum from n equals 3 to infinity of 20 over n plus 1 C3 minus 1 over n plus 2 C5 is less than 5 factorial over n cubed. And if you remember, we already know what the sum of n equals 3 to infinity of 1 over n plus 1 C3 is. If you remember, it is just a half. So this left-hand side essentially becomes, for here, 20 multiplied by a half minus the sum from n equals 3 to infinity of 1 over n plus 2 C5 is less than, sorry, I forgot the sum here, the sum of n equals 3 to infinity is less than the sum from n equals 3 to infinity of 5 factorial over n cubed. So now let's deal with this sum over here. So just like we did in the last part, we need to somehow change this into a form that can be evaluated, because if you remember, if I scroll up, we need it in this form: 1 over n plus r c r plus 1. So r plus 1 has to be equal to 5, which means r has to be equal to 4. So we need n plus 4 up here. However, of course, we don't have that. We have n plus 2. So, if we look at the first term of this sum, it'll be 3 plus 2, which is 5. So 1 over 5 C5. And if we want to make this n plus 4 C5, then we need to start the sum from n equals 1, so that the first term is 1 over 5 C5. So this sum here is the same as the sum to infinity of n from n equals 1 to infinity of 1 over n plus 4 C5. And if we use our sum, which is r plus 1 over r, this is going to be equal to 5 over 4. So, if I scroll down again, what we have now is 20 times half, which is 10, minus 5 over 4 is less than the sum from n equals 3 to infinity of 5 factorial over n cubed. And if we simplify the left hand side, that'll give us 35 over 4 is less than the sum from n equals 3 to infinity of 5 factorial over n cubed. So if we play the same trick as last time and add the first two terms of the right hand sum to each side, we will get 35 over 4 plus 5 factorial over 1 plus 5 factorial over 8 is less than 5 factorial over 1 plus 5 factorial over 8 plus the sum from n equals 3 to infinity of 5 factorial over n cubed, which is equal to the sum from n equals 1 to infinity of 5 factorial over n cubed. If we then, so what we could do is add up the left-hand side of the inequality and then divide both sides by 5 factorial. However, it might actually be easier if we divide by 5 factorial first. So this will give us that the sum from n equals 1 to infinity of 1 over n cubed is greater than 35 over 4 times 5 factorial plus 1 plus 1 over 8, which is equal to 115 over 96, which is the left hand side of the inequality. And so all in all, we get the required result, which is that the sum of from n equals 1 to infinity of 1 over n cubed is greater than 115 over 96, which in turn is also less than 116 over 96.